Welcome all to this session of magnetic materials. This is the fourth session in magnetic materials. So in the last module, we described about the hysteresis curve or pH curve exhibited by either ferro or ferrimagnetic materials. Now in the last module, so what we have to describe is to be what are the differences between hard to soft magnetic materials and problems in magnetic materials. So what the contents in magnetic materials are to be basic definitions, origin of magnetism, types of magnetic materials, BH curve or hysteresis curve, hard and soft magnetic materials and problems. In the first three modules, I covered the previous topics. Now we have to distinguish between hard and soft magnetic materials. As the application of hysteresis loop, it is possible to distinguish between hard and soft magnetic materials. So a few points are there that we have to see here. So hard to soft. First hard we have to see first point. Hard magnetic materials have large hysteresis loss. Hysteresis loss is nothing but energy loss. Then hard, name itself is indicating these are hard. Hard means it is very difficult to magnetize the material. To magnetize the material it takes time and large strength of magnetic field is required. But once they get magnetized, long time it is retained by the material, and demagnetizing that material is also to be difficult. That is why the name of these materials itself is to be hard. So for the cycle of magnetization and demagnetization, energy lost by the material is more. So that we call it as hysteresis loss. How it is to be large. And next same point for soft magnetic materials is these materials have low hysteresis loss. So how much is the energy lost by the material is to be low. The name itself is indicating these are soft. Soft means once the external magnetic field or external energy is applied, materials get easily magnetized. And once we have to remove the external energy or magnetic field, easily they can get demagnetized. So easy magnetization and demagnetization cycles are available. So for the soft is exhibited by the soft magnetic material. So automatically energy lost by the material is to be low. Energy loss is nothing but hysteresis loss. How it is for soft magnetic materials is low. Then domain wall movement is difficult. So how the domain wall movement we can describe here is to be to get the magnetization or demagnetization by the material, domain wall movement is compulsory. As the material is hard, domain wall movement how it is to be difficult. Then soft magnetic material, how the domain wall movement is here is to be easy. Easily domain wall movement to be taken place. That is why cycles of magnetization and demagnetization are easy in soft magnetic materials. Then next is to be coercivity and retentivity are large. Then model hysteresis diagrams we have seen for the hard magnetic material and soft magnetic material. We have known, so that diagrams we have to see. These are the examples for hard and soft. Then hysteresis loop we have seen. This is origin. Then this is O2A saturation point. OB is retentivity and OC is coercivity. This is retentivity distance. It is high, and coercivity distance is also to be large for hard magnetic material. Large for hard magnetic material. OB and OC distances are high for hard magnetic materials. Then what happened to soft magnetic material? Again this is O. Then area of hysteresis loop is to be very small for the soft magnetic material. Then O. Then this is B. OB small it is to be. OB is to be high. Somewhat OB is also to be large. Means retentivity is also large for soft magnetic material. Retentivity is high, but what about OC here? Coercivity is small. OC is small. So OB is large, OC is small. Here both OB and OC are high for hard magnetic materials. By seeing the model diagrams only, it is possible to write this point here. Coercivity and retentivity both are large for hard magnetic material, and here both are small, it should be given, it is wrong. Retentivity is high. Retentivity is vertical distance, that is O to B, it is high, and coercivity OC is small. To erase that retentivity, field required is small in the case of soft magnetic material. Observe this correction here. Next point, cannot be, hard magnetic materials cannot be easily magnetized and cannot be easily demagnetized. These are hard, it is not possible easily. Then soft magnetic materials can be easily magnetized and easily demagnetized. Next, magnetostatic energy is large. In the case of hard magnetic materials, magnetostatic energy is large. And in the case of soft magnetic materials, this magnetostatic energy is small. Then hard magnetic materials have small values of permeability and susceptibility. This already we described. Permeability is mu, susceptibility is psi. Permeability is number of lines of force. As difficult to magnetize and demagnetize, less lines of force we expect here. So permeability value is less. Susceptibility is easiness of magnetization. No easiness is there. So susceptibility is also low. Permeability is also low. Then these are soft magnetic materials. These have large values of susceptibility and permeability. So susceptibility is also high and permeability is also high for the soft magnetic material. Then these hard magnetic materials are used to make permanent magnets. Why these are used to make permanent magnets here is to be, once they get magnetized, then for demagnetization also they have to take long time. To get demagnetization also, it is very difficult to demagnetize the hard magnetic materials. So that is why they can be used as permanent magnets. Then soft magnetic materials can be used to make electromagnets. Once electromagnets means electrical energy we have to give, they will behave like magnet. You remove the electrical energy, then they will get demagnetized. Like that, in the preparation of electromagnets, we can use soft magnetic materials. Examples for hard magnetic materials are iron, nickel, aluminum alloys, copper, nickel, iron alloys, copper, nickel, cobalt alloys. And soft magnetic materials are iron, silicon alloys, ferrous, nickel alloys, ferrites, garnets. One ferrite we have known, that is nothing but magnetite, Fe3O4. That is also coming under the example for soft magnetic material. Magnetite, that is ferrite, is the example for soft magnetic material. Then examples for hard magnets are alnico, copper, nickel, cobalt. Here are the some of the formulas I have written for the examples of hard magnets. Alnico, copper, nickel, cobalt, copper, nickel, iron, manganese, bismuth. All these are alloys, examples for hard magnets. Then for soft magnets, permalloy, supermalloy, permandur, permandur. These are nothing but iron, nickel and iron silicon alloys. Among all this, which is the best permanent magnet is alnico. Alnico, aluminium, nickel, cobalt is the best permanent magnet. Then applications of hard magnets. So where these hard magnets are used are in microphones, in magnetic separators, in measuring instruments. Magnetic separators means in iron based industries to separate iron based components. These hard magnets are used as magnetic separators. In measuring instruments like voltmeter, ammeter, wherever the magnet is required, hard magnets are used. In voltage regulation purpose for the various circuits, hard magnets are used. Then as permanent magnets, we can use this one. Applications of soft magnets in transformer cores, electromagnets, electromagnetic coils. In switching circuits, soft magnets are used. So these are some of the differences between hard magnets to soft magnets. And at last, we have to see the problems. To solve the problems, first we have to write what the basic formulas in magnetism. So magnetic dipole moment, M is equal to M into 2L. 2L is the length of the magnet, M is pole strength. Magnetic flux density is flux by area, phi by A. Field intensity H is equal to force per pole strength, F by M. Intensity of magnetization I is equal to dipole moment per unit volume. Same formula pole strength we have to write in terms of pole strength is M by A, pole strength per unit area. Xi susceptibility is equal to I by H. Permeability mu is equal to B by H. Relative permeability mu R is equal to mu by mu naught, where mu naught is permeability of free space. B is equal to mu naught into H plus I. Relative permeability mu R is equal to 1 plus Xi. These are the formulas. Then using these formulas only, we have to solve the problems. First problem, find the relative permeability of a ferromagnetic material if a field of strength 220 ampere per meter produces a magnetization of 3300 ampere per meter in a material. What we have to find out is relative permeability we have to find out. For that, first we have to write what are the given values here. So given values are magnetic field strength is 220 ampere per meter. External magnetic field intensity H is equal to 220 ampere per meter. Then intensity of magnetization I is equal to 3300 ampere per meter. Then H and I values are given. Relative permeability formula we have known. Mu R is equal to 1 plus Xi. 1 plus Xi. 1 plus Xi is I by H. I by H values are already given. 3300 by 220. Then after solving this, how much is relative permeability is 16. No units for relative permeability. So this is the first problem. And the second problem, coming to second problem, magnetic field in the interior of a solenoid has the value of 4753 ampere per meter when it is empty. When the solenoid is filled with the iron, it gets magnetized and the flux density of iron is 0.1756 Tesla. Find the relative permeability and susceptibility of iron. So we have to find out both relative permeability mu R and susceptibility Xi of the iron. For that, first we have to write the given values. H is equal to, when solenoid is empty, how much is the magnetic field it is produced is H is equal to 4753 ampere per meter. Then when it is filled with iron, whose magnetic flux density B is equal to 0.1756 Tesla. Then first we have to find out permeability mu is equal to B by H. Then B by H is like this, 3.6945 into 10 power minus 5 Henry per meter. Then mu R we have to find out. Mu R formula is mu by mu naught. Mu already we calculated. Mu naught is standard value. That is 4 pi into 10 power minus 7. That is the permeability of free space. Mu by mu naught, if it is calculated, 29.41. No units for this. Then mu R is equal to 1 plus Xi. We want to calculate Xi here. Then Xi is equal to mu R minus 1. Mu R is 29.41 minus 1 is 28.41. Xi is equal to 28.41 and Xi is also having no units here. So that is the second problem. Next, third problem is a magnetic material has a magnetization of 3300 ampere per meter and flux density of 0.0044 Weber per meter square. Calculate magnetizing force and the relative permeability of the material. Here also two values we have to find out. Magnetizing force is H and the relative permeability is mu R. For that, in the problem, what the values are given are, I, intensity of magnetization is 3300 ampere per meter and flux density B is equal to 0.0044 Weber per meter square. We have this relation among three magnetic parameters B, H and I. B is equal to mu naught into H plus I. Then we want to calculate H here. We have to rewrite this formula for H. H is equal to, taking this mu naught to left hand side, H is equal to B by mu naught minus I. Then B and mu naught values we have known, minus I is 3300. Then H is equal to 203 ampere per meter. Once H we calculated, mu R is equal to 1 plus Xi. 1 plus Xi is I by H. I already given in problem 3300, H is 203. Then value for relative permeability is 17.5 and no units for relative permeability. This is the procedure for third problem. Next, last problem. A circular loop of copper having a diameter of 10 centimeter carries a current of 500 milliampere. Calculate the magnetic moment associated with the loop. So here is the circular coil of copper. Then it is carrying current. How much is magnetic moment associated with it? So magnetic dipole moment notation is mu. Mu formula here is to be I into A. How much is current carried by into area of the circular loop. So to calculate area is pi r square here. So we want to get radius. For the diameter information, it is given in problem. Diameter d is equal to 10 centimeter. In meter it is 0.1 meter. Then radius is 5 centimeter or 0.05 meter. I current is 500 milliampere. Milli means 10 power minus 3. In amperes, if we have to write 0.5 ampere. Magnetic moment associated with the circular loop formula is mu I is equal to A into I or I into A. A is pi r square. Pi means 3.14. R square is 0. R is 0.05 into 0.05. Why? Because square is there. I is 0.5. After calculation, we'll get mu is equal to magnetic dipole moment 3.93 into 10 power minus 3 ampere meter square. So this is the last problem. Next problem is also there. Fifth problem is the magnetic susceptibility of silicon is minus 0.4 into 10 power minus 5. Calculate the flux density and magnetic moment per unit volume when magnetic field of intensity 5 into 10 power 5 ampere per meter is applied. So flux density we have to calculate. B is equal to how much we get calculated, and magnetic moment per unit volume, nothing but intensity of magnetization, that is moment per unit volume. How much of this we have to calculate? For that, what values are given? Susceptibility of silicon, Xi is equal to minus 0.4 into 10 power minus 5 Tesla. Here minus value is there. Susceptibility means which type of magnetic material it is to be? Diamagnetic material. That is minus 0.4 into 10 power minus 5 Tesla. Then given field intensity H is 5 into 10 power 5 ampere per meter. Then first flux density formula is mu naught into H plus I. Then multiplying this mu naught H into 1 plus H we have to take out from bracket here. Then mu naught into H taking outside the bracket. Mu naught into H then into 1 plus I by H. 1 plus I by H is written as Xi. Then mu naught is 4 pi into 10 power minus 7, H already given, into 1, Xi value is minus 0.4 into 10 power minus 5. Then after calculating this, how much is flux density? 0.62 Weber per meter square. Then B we calculated intensity of magnetization. Xi is equal to I by H. I is equal to Xi into H. Xi already given. H we have known 5 into 10 power 5. Then minus 2.0 ampere per meter. Intensity of magnetization is also negative for diamagnetic material. Units are ampere per meter. So this is the fifth problem. Then thank you all. So this is the last module in magnetic materials, where we have described soft and hard magnetic materials and what are the problems in the magnetic materials that we have described. Thank you all.